Hello and welcome to Chemical Interactions, Year 8. This is Lesson 2, Molecules. So today it's Mrs. Castanera here. We'll be going through a lesson on molecules. Today's key words are at the top of the page. You should all have a copy of this that's been sent to you. The key words are atom, element, reactive, shell, valence electrons, covalent bonds, share, and molecule. You need to know all of these to fully access the lesson. So your first task is to attempt the knowledge check questions at the start of the lesson. I'd like you to pause the video, answer the questions please, and then we'll go over them together. Okay, so let's go through those questions. Question 1. The electrons found on the highest energy level are the valence electrons. Make sure you're using another colour to correct or to tick your work. 2 nonmetals will share some of their valence electrons. Nonmetals will try and gain electrons to fill their outer shell. If 4 electrons are shared, we say there is a double covalent bond. A covalent bond is a shared pair of electrons. A covalent bond only forms between 2 non-metals. Covalent bonds are very strong. And the charge of non-metal ions is negative. And that's because the non-metals gain electrons, which makes them more negative, as electrons are negatively charged. So make sure you have ticked or corrected all your answers, please, and give yourself a mark out of 8. Okay, so today our plan for the lesson is to be able to define and give examples of molecules. So this is what we need to be able to do at the end of the lesson. So what is a molecule? Well, atoms will combine together in 2 ways in order to fill their outer shells. So there are 2 different ways. The first way is through ionic bonding, where metals lose electrons to become positive ions, and then they are attracted to the negative ions from nonmetals that have gained electrons. So metals lose electrons to become positive ions, and then they are attracted to the negative ions made from nonmetals that have gained electrons. So for example, Na+, that's a sodium ion, which is positive, and chlorine or Cl-, a chloride ion, which is negative, they join together to make sodium chloride, which is the table salt you would put on perhaps your chips at home. Then the other method, which we'll be looking at in more detail, is covalent bonding. So covalent bonding, as we learnt last lesson, is when non-metal elements share pairs of electrons to fill their outer shells. So those are 2 methods. Now it's very important to remember that covalent bonding is non-metals, whereas ionic bonding is a metal and a non-metal. So this is metals and non-metals. Okay, and it's the ions of the non-metal and the metals. Okay, so a molecule is when 2 or more atoms are bonded together. So 2 or more atoms bonded together, that is what a molecule is. Now we have some examples of molecules here. These are all molecules, but there is a slight difference between them. So molecules such as this, N2, that means there are 2 nitrogen atoms bonded together. Another example like this is 2 hydrogen atoms bonded together. These are elements. They are the same type of atom bonded together through covalent bonding. So these are elements, which are the same type of atom bonded together. So on this side, over here, we have some molecules which are made of more than one type of atom. So not the same type of atom bonded together, but different types of atoms bonded together. So for example, CH4, also known as methane, has carbon molecule and it's got 4 hydrogen molecules. That's what that little 4 means. So this here is an example of a compound. Okay, so a compound is different types of atom bonded together. Now, both elements and compounds are types of molecules. And molecules are the big category, and compounds and elements are 2 different types of molecule. So as it says here, these examples are made of more than one atom bonded together. That's what molecules are. Okay, they're all made from non-metals because ions don't tend to form true molecules, but we're not going to worry about that. So molecules can have the same or different types of atom. So if it's the same type of atom, it's an element. If it's a different type of atom, it's a compound. So now we're going to move on to activity 1 on the next page. You will need to keep this page handy because you're going to use these examples of molecules to complete table 1 shown on the next page. Now, you will need to identify 4 elements and 4 compounds. So, one of our examples from the previous page of an element was N2. So we can fill in N2 as an element because it's atom of the same type. On the other side, we had CH4, an example of a compound, so we can write that in the compound side. Now what I want you to do is I want you to complete this table, pause the video whilst you do so. Okay, so here are the answers that we'll go through together. So N2 we should already have. H2, I2 and Cl2 are all elements. They all contain one element, one type of atom. There's just 2 of those atoms. They are still molecules though. And compounds include H2O, known as water, CO2, carbon dioxide, NH3, known as ammonia, and CH4, known as methane. So remember that molecules are 2 or more atoms bonded together. So a molecule is 2 or more atoms bonded together. So 2 or more atoms bonded together. If those atoms are the same element, they're the same type, then they are elements. If those atoms are different elements, different types of atoms, then they are compounds. Those are the 2 types of molecules. Now we're going to have a look at some everyday example of molecules. So first of all, we have table salt. And you may recall from earlier, table salt can also be written as NaCl, sodium chloride. Now, table salt involves ionic bonding between the metal sodium and the non-metal chlorine. So that's ionic bonding between the metal sodium and the non-metal chlorine. And in fact, you can see in this diagram, the structure here is an alternating arrangement of positively charged ions, which is the sodium ion, and negatively charged ions, which is the chloride ion. So it's Na plus and Cl minus are the 2 ions that we see. And they have this interlocking arrangement here where they form a tightly knit pattern of alternating charges, And that's because each charge is attracting other atoms of the opposite charge, and each charge repels atoms, or ions in fact, of the same charge. So remember, like charges repel, opposite charges attract. And this structure is called a giant ionic lattice. And that's what this very large structure is. And these can get millions and millions of atoms in one enormous structure. So they get very large. And they are positive and negative ions, alternating and interlocking. And we call this structure crystal or crystalline structure. So we're going to write here that there is an alternating arrangement of ions. Now, moving on to this one here. This is sugar, also known as sucrose. There is more than one type of sugar. Not that you need to worry too much about the other ones. So the chemical formula for this is C6H12O6. So we'll just highlight that. I'm going to write that out again at the bottom nice and large. So C6 means there are 6 carbons, H12 means that there are 12 hydrogen atoms, and O6, which means there are 6 oxygen atoms. And the arrangement of these atoms, which is what makes sugar or sucrose look like this. This is the arrangement of the atoms. Each of these rings, we call these hexagons rings in chemistry, is made from carbon, with the exception of this oxygen molecule here. The oxygen atom here is connected to a ring of carbon, and then there's this second ring of carbon also with an oxygen atom in it, and they are bonded together with an oxygen atom. So we will talk about these as 2 rings of carbon that are joined together. Now, sugar is made from nonmetals because carbon, hydrogen, and oxygen are nonmetals, and we already know that nonmetals bond covalently. Now, this sugar is formed during photosynthesis, which is when plants use sunlight to turn carbon dioxide and water into glucose. Now, you can tell this is made from carbon dioxide and water, partly because carbon dioxide is made from carbon and oxygen atoms, and water is made from hydrogen and oxygen atoms. So sugar is made from those 2 products exclusively, and sunlight provides the energy for this reaction to occur. So let's talk about water. It comes from the soil beneath the plant, and the carbon dioxide comes from the air around the plant. And oxygen is produced because there is more oxygen in the carbon dioxide and the water than we need. So spare oxygen is made, and that is the waste product, which is why we enjoy having plants in our environment, because it provides us with an increased amount of oxygen in the air for us to breathe, as oxygen is essential to human survival and human breathing. So I'm going to move on to DNA. DNA is a 3-letter acronym. That means it's 3 letters that mean something else. They stand for something else. And they stand for the D in deoxyribo, N, nucleic, and A in acid. So DNA is short for deoxyribonucleic acid. That is a mouthful, so we call it DNA. And it's a molecule, which means it's made of more than 2 atoms bonded together, and it is found inside all of your cells. And it's made from something called amino acids. And these amino acids are bonded together. So it's made from amino acids bonded together. Now, the sequence or the order of these amino acids is what gives us our genetic code. Everybody's genetic code is unique. That means we all have our own code different to that of someone else. So it gives a genetic code, okay, and we have our own unique code. However, there are a couple of exceptions to this, the main one being twins. So identical twins will have the same genetic code. So that's the main exception to that. So PVC. Sorry, there's one more here. We want to write about the shape. Now, the shape of this is called a double helix. Now, the double helix refers to the fact that it's a twisting shape, or helical, and also that it is like a ladder. It has two long chains. That's the double part, because there are two long chains which are joined together by these little ladder-like rungs. So we're going to move on to PVC. PVC is another acronym. So PVC stands for polyvinyl chloride. And it's a chain of monomers which are bonded together. So polyvinyl chloride, PVC, is a chain of monomers bonded together, and that makes one very long molecule. And these long molecules all intertwine, get tangled up, and they turn into PVC plastic. Now, you can see here the repeating pattern. This is not the monomer. Okay, the monomer is the shorter part that repeats over and over and over again, hundreds, thousands, maybe even millions of times to make a very long chain. And I'm going to show you, and we'll see if we can work out this together, but there's carbon chain here, and then there's hydrogens all along the bottom, and the top part alternates between hydrogen and chlorine, hydrogen and chlorine. And in fact, if we wanted to, we could break this up into sections here, here, here. And each of these four sections are identical. And that is what the monomer is. It's the identical repeating section. So our identical repeating section, our monomer, is carbon, carbon, and then a hydrogen, a chlorine, a hydrogen, and another hydrogen. And I'm going to use black now because I need another pen colour to show this clearly. I'm going to put this in brackets. And these side bonds here are very long. They go outside the brackets, and they show that this can be joined together as many times as you like. And in fact, we also put the letter N here. Now, in this case, N demonstrates and represents that this monomer can be repeated N number of times, so any number of times, as many times as we like, in fact. So we're going to say that this is the repeating monomer, and this is the repeating monomer for PVC. Other long chains will have different monomers. And N represents how many times it can be repeated. When we write N, it means it can be repeated any number of times. So N shows that it can be repeated. Right, so we're going to move on now to diamond. Diamond is one of the hardest substances known to man. It consists of carbon atoms, just carbon. So it's one of the hardest substances known to man. It is just made from carbon atoms. Each carbon atom has 4 covalent bonds. Now, covalent bonds are very strong bonds, and so diamond is very strong. It forms a giant covalent lattice. This giant covalent lattice, which is its 3-dimensional structure, is all about its shape, and that makes it very much stronger than you would expect and much stronger than other forms of carbon. So I'm going to write here that it's strong 3D structure of carbon atoms. So the strong 3D structure of carbon atoms makes diamond so hard. I'm going to move on to graphite now. Graphite is also made from carbon, just carbon. Very different form of carbon to diamond, much cheaper, for instance. Now, this time, each carbon atom only has 3 covalent bonds. If you remember diamond, every carbon atom had 4 covalent bonds. So this time, they only have 3 covalent bonds. Now, this means that these molecules of these carbon atoms are arranged into layers. So this here shows us one layer of carbon atoms, and each of these individual layers can slide past each other. So that means that the graphite is really useful for purposes where you want the layers to slide off. So pencils, for example, we want a layer of carbon to slide off on our pencil because when we use it to draw, we want some of the carbon, the graphite, to be left on the page. That is a very useful property of graphite, which I've just used with my pencil. We also use graphite as a lubricant, a dry lubricant, not like oil or water, but a dry lubricant, which can be used in machinery. And again, the property of it being able to slide past itself in layers is what makes it useful for that purpose. So we're just going to write here that this here is representing one layer of carbon atoms in a thin sheet. And these dotted lines here represent the weaker bonds. Okay, so these are weak intermolecular bonds, or intermolecular forces. So these are the weak intermolecular forces between layers of graphite. And it's these weak forces that are overcome when the layers slide past one another. So now we're going to move on to the next ones on the next page. So the first thing we're going to look at is silicon dioxide. Silicon dioxide, also written as SiO2, which we're going to write for ourselves. SiO2 also has that strong three-dimensional shape similar to diamond, which is the first thing you'll probably notice about this. It forms that giant covalent lattice, just like diamonds. It's not as strong as diamond. The main reason for that is because it's made from slightly different elements. This time it has silicon and oxygen in it rather than just carbon. But it is very hard still. It's also more commonly known as sand or quartz. So we're going to write here a little note. See, it's got that strong 3D structure like diamond. And as I'm sure you will recall, sand is very tough. It's hard to destroy sand, and it's hard to destroy quartz crystals. But it is not as strong as diamond. And our last compound is methane. So methane, which we've talked about before, it's a simple covalent molecule, which means it just has covalent bonds. It's only got 4 atoms. It is a gas at room temperature, and it's commonly used as a fuel. It's the main fuel we use if you have a gas cooker or gas hob at home, or if you have gas heating at home. It's used in our gas taps at school and gas at home. Now, we're going to write this as its chemical formula. So capital C to represent the carbon, capital H to represent the hydrogen. There are 4 hydrogen atoms, so we put a 4 after that. And this gas can be used for cooking food by burning the gas. So we're going to write a little thing to say we burn this gas as fuel. Okay, so you'll need to go back and make sure you've got all the notes that I have and that you're happy, confident and understand each of these items. If you're not sure about one of these substances, feel free to just pop the word, the title into Google, so silicon dioxide, for example. If you type that into Google, you'll be able to find lots of different options that will tell you all about both the compound and its properties. So now we're going to move on to learning activity 3, modelling simple molecules using monomers. Now, we're delivering this lesson from home and do not have monomers. However, I have improvised and we're going to do this with some Play-Doh. If you happen to have Play-Doh, feel free to join in. So, you're going to need to know a bit more about what you're going to need in terms of Play-Doh and equipment. So we're going to be building these molecules here: hydrogen, oxygen, water, methane and carbon dioxide. So, things to know before we start building. Each colour represents a different element. So, for example, I have produced little Play-Doh circles in red, white and blue. Now, I've had to make do here because white represents hydrogen. So this is my hydrogen. Red represents oxygen. So here's my oxygen. And black represents carbon. Now, I don't have black Play-Doh, so I've used blue. Now, normally blue represents something else. We're not going to worry about what. But today, for this one, we're going to use blue for the carbon. However, in our diagrams, because we're going to draw each of these, you're going to want to use the correct colours. Now, normally, we'd have grey bonds, and these balls would be made of plastic and they'd have holes in them, and you'd have to fill each of the holes with a bond and know that it had used up all of its potential attachment points. Now, because we don't have this, I've been using some straws. I literally took a straw and chopped it up into small pieces. Okay, so that's what we're going to do. So here is my hydrogen atom. In fact, I think I'll do this on a red background. So here is my hydrogen atom. And H2 is two hydrogens bonded together like so. I'll put that to one side. It breaks. There we go. Put that to one side. Now, the next one we're going to build is O2. So I need two oxygen atoms. And we'll do this on a red background now. So two oxygen atoms. And I need a bit of plastic straw to join them together. You could use a bit of cocktail stick, anything you want really. So there is my O2. Now, it's not as simple as that, I'm afraid, because oxygen, as you remember from last lesson, has a double bond. Okay, so it shares two pairs of electrons. So in fact, we can't just join it with one straw. No, we must use two. So that is my oxygen correctly bonded together. I'm going to label these, I think, as we go. So this is H2. This is O2. So our next one that we're going to do is H2O, also known as water. So here's my oxygen atom and my two hydrogen atoms. And again, if you have a... Oh, we haven't drawn that one recently. Well, the way this one goes together... Oh, we have drawn it. So if we have a look at what we did before, you'll see that the hydrogen atoms are off to one side and the spaces are on the other side. So we're going to try and replicate that shape with our model. There's a reason for this, and you'll learn more about that next lesson. Now, oxygen and hydrogen bond with just one pair of electrons. There we go, and there is my H2O water. Okay, our next molecule is CH4. Now, we need a carbon centre. So remember, it's supposed to be black. And we need 4 hydrogens. So here are 4 hydrogen molecules to attach. And I need to stick a little bit of straw in each of them and attach them. Now, last lesson, we drew this like so, with them all spread out. Now, because we drew on paper, this is a two-dimensional representation. And because we're still in Year 8, that is absolutely fine. And it will probably still be fine at GCSE. Eventually, if you go on to do A-level chemistry or beyond, you might need to know a little bit more about the three-dimensional structure of this bonding and what it actually looks like. So for now, you can make it look like this. Let's move that up so you can see it better. So for now, you can make it look like this, but the reality of the situation is that in order for these hydrogen atoms to get as far away from each other as possible, what it actually looks like in 3 dimensions is, this is probably going to break, but the 3 hydrogens form a sort of tripod which lifts the carbon off the ground and up above them, and then the last one goes on top, and it forms a sort of pyramid shape. And I will attempt to show you this. So it's not perfect. My pyramid should have a slightly wider base, but it should look a little bit like this. And this is going to fall apart on us because, Play-Doh. But that's the reality of it. So I'm going to put it back to its 2-dimensional shape because it's very difficult to draw in that 3-dimensional shape, and it's absolutely fine to use it in this 2-dimensional arrangement as we did before. So we'll leave that there. Rather poorly put together. There we go. And that is CH4. So 1 carbon with 4 hydrogens attached. And our last compound is going to be carbon dioxide. So 1 carbon with 2 oxygens. And again, looking back at last lesson, you'll remember that carbon dioxide has got 2 sets of double bonds. And we need to represent that. So the way we're going to do that is we're going to take our 2 pieces of straw and we're going to attach them to our carbon and our oxygen and bond them. And same on the other side. And then we have our carbon dioxide. So your next task is, if you want to make them with Play-Doh or whatever you've got, great. But regardless of that, I would like you to draw each of these. So for example, this is how I've drawn hydrogen. Okay, so representing this hydrogen with literally 2 circles with an H in, joined by a line. And then for something with a double bond, such as this oxygen, again, 2 circles. I've identified them with the letter O to represent the oxygen, coloured in red, and with a double bond. When you get to carbon, make sure you use black, please. So this one would be methane. So what I want you to do is pause the video. I want you to draw your own version of these, please. And then once you've done that, you can unpause and we'll carry on. And I'll show you my version of each of these. You can either pause the video now and have a look at them afterwards and compare them to yours, or you can carry on watching and then pause after I've shown you my versions. So these are the ones I did. So as you can see, you've got hydrogen, white circles with a single bond. You don't have to write the H on, that's not necessary. Great if you did though. The oxygen, so again, 2 circles with double bond in the middle. Now I've drawn my oxygens bigger just because I know that oxygen is a bigger molecule than hydrogen. Here we have water, so the oxygens and the hydrogens connected by a single bond. Then we have carbon, remembering that carbon has to be a darker black molecule, not blue. And again with the double bonds and the shape where they have gone closer to each other, which we did show. Then we've got methane, so the carbon atom surrounded by the 4 hydrogens. If you've tried to represent that in 3 dimensions, well done, don't worry about it. If you haven't, also well done, don't worry about it. So make sure you've got each of those, please. So now we're going to move on to the last little section of the lesson, which is all about simple molecules. So the models you have made, or that I have made, were constructed of a small number of atoms. They didn't have very many, only a few. Now the covalent bonds between the atoms are very strong. But there is also another type of force, an invisible force called intermolecular force. Now it's not really enough of a force to be called a bond, but the intermolecular forces occur between molecules, and they are very weak in comparison. So our simple molecule is made of a strong covalent bond with weak intermolecular forces between them. These intermolecular forces attract the individual molecules to each other. So individual water molecules are attracted to each other by these intermolecular forces. The same goes for any molecule. Most simple molecules exist as gases or liquids at room temperature. And something we need to say is that about size of these atoms. So the bigger the atom, size of the molecules, the bigger the molecule, the larger the intermolecular forces between them. I'm going to write that down. So the bigger the molecule, the larger the intermolecular forces. Okay, so the bigger the molecules, in fact, because you need more than one molecule to have intermolecular forces between them. So the bigger the molecules, the larger the intermolecular forces between them. So small molecules such as hydrogen or water will have very few and small intermolecular forces between them. Much larger molecules such as PVC, the polyvinyl chloride, the big long chain of monomers, they're going to have a lot more intermolecular forces between them, and that's going to have a much stronger influence and exert a lot more force because there's so many of them. So what I'd like you to do now is to pause the video and have a go at the knowledge and application check, please. Okay, so let's go through the knowledge and application check questions. Name 2 ways that atoms can bond. They can bond through either ionic or covalent bonding. There are other types of bonding, such as metallic bonding, but we're not looking at those right now. If you said intermolecular forces, that would not be a correct answer. Question 2. Molecules are made of more than one atom bonded together. So more than. If you can use a pen in another colour to tick or correct your answers, that would be wonderful. The 2 main groups of molecules are elements and compounds. The force between simple molecules is intermolecular force. The bond between nonmetals is covalent bond. Name the strong bond in simple molecules. That's also covalent bond. Question 7. There are 2 electrons shared in a covalent bond. Any more than 2 and it would be a double covalent bond or even a triple covalent bond. The 2 states of matter that simple molecules usually exist at room temperature is gas or liquid. And predict the relationship between the size of a simple molecule and the strength of the intermolecular forces. Okay, so the answer to this is the larger the molecule, the stronger the intermolecular forces are. Okay, so make sure you've ticked your answers and give yourself a mark out of 9, please. So if you could go ahead and take photos or a screenshot of the work you've completed and email it to your teacher, please, that would be wonderful. Thank you very much. of